Oh, okay. Yeah. Welcome back, guys, to the last recitation. I'm going to remind you that next week I'm doing a review recitation on Tuesday. I'm going to send you guys the time, but I'm going to be doing a review recitation in Hebrew and try to go through as much as the material that I can get through while solving questions. So just reminding you that there's that. Um, If I don't see you then good luck on test, everyone. Everyone in the recordings, everyone here. Good luck. I really hope it goes well. Give a few tips for the test at the end of this recitation. So this week we're learning greedy algorithms. We already learned it in the lecture. You went over a couple problems, including Hoffman coding. We're going to do more problems that are what we're going to expect you to be able to do by yourself on test questions. Um, Obviously, we could still expect for you to know Hoffman coding, but we're not going to expect you to come up with Hoffman coding by yourself. But for these kinds of questions, we might give you a problem that you haven't seen before and expect you to realize that you can use greedy for it. So let's just see how we're going to do this. So first off, a paradigm is some sort of way of thinking, and in algorithms, it's a way of planning. Um, it's a way of planning algorithms. It's something that you can use to solve many different algorithms. Um, and it's useful for algorithms for problems of the same type in the future. So we saw like divide and conquer. It's the same paradigm that we can use for many different problems. Um, Not just the ones that we saw in the class. There's also other problems which come homework and so on and so forth. It's a way of thinking. So we already saw two, and we're going to see the last one today, which is greedy algorithms. So first off, what is a greedy algorithm? Can you guys answer that from the class? What's a greedy algorithm, Thomas?
The way that option is done.
Whatever option it can? Let's take exactly. It takes the optimal option locally based on the data that it has right now. So definition is a greedy algorithm. It's a paradigm, right? Like we said, that every single step takes the optimal local decision, which is basically based off of the information it has right now. It makes the best decision that it can. And then it hopes that in the end that'll lead to an optimal solution, right? It's just what we said in simpler words. It just takes the best option right now and hopes that it gets to a better solution at the end. So a couple of qualities of properties of greedy algorithms. It makes decisions based on only current information it has. It doesn't plan into the future. It doesn't calculate what will happen if. It just makes a local decision. It never goes back on decisions. Once you make a decision, you're stuck with it. There's no going back. And it is very easy and intuitive to implement. Once you have the algorithm, it's usually a very simple, in pseudocode, it's 5 or 6 lines of code. And usually it's very, very, very efficient as opposed to other algorithms. If you try to do a divide and conquer, it would take a whole lot longer.
Do you send that name? So I didn't get it.
You didn't get it?
Thanks.
Thanks. Pause the recording. Very important. All right. Up and down has just been really an intro, but they're usually very efficient. Because they make a decision based on information they have right now. They make a very simple decision, which takes not so long to compute.
It's okay. So sort it or
It might have to sort, yeah. A lot of times it does sort. That's why it's a lot of times in log n. But sometimes if you don't have to sort it, then it's it O of n. So every time it makes a decision, it usually takes it O of 1 because it makes it just based off of that. Okay. Second. Okay. Okay. Do we have a greedy algorithm for every single problem? No. Why not? You guys are right. It's not. We don't have a greedy algorithm for every problem.
So problems are more faster.
Some problems are more global.
If they rely on.
Yes, that some problems you can't make the decision right now. If you make the optimal decision right now, it'll ruin all your optimal decisions. There are cases where certain problems, and we'll see. We'll talk about some of those in a little bit. So when do we have a greedy algorithm? All right, so let's talk about when we do have a greedy algorithm. So we have two qualities, two properties. First one is the greedy choice property, which is that there exists some sort of optimal solution that starts with our greedy choice, right? So if our greedy algorithm chooses the largest of the elements, then we have to prove that there exists optimal choice that includes our choice, an optimal solution that includes our greedy choice of the largest element. Because it could be that we just ruined all of our solutions. And the second one is the optimal substructure quality. That this property is basically, this isn't enough to say, because this is basically saying that there exists some solution with our greedy choice. And this one is that given optimal subsolution of our subproblem without the greedy choice, if we take away everything but the greedy choice, and that is given an optimal solution. So that combined with our greedy choice together makes an optimal solution to the whole problem, right? So we're taking our greedy choice. This is saying that our greedy choice doesn't ruin our solution. And this is saying that there still exists some optimal solution with our greedy choice. And this one is saying that if you take our greedy choice with an optimal solution to the rest of the problem, together, if you combine them, we will get an optimal solution to the problem. And this is also how we prove the correctness of our greedy algorithms, which we're going to do a couple times in this recitation. So first question is the politician problem, also called the activity choosing problems. Basically, our politician is competing in elections, and he wants to get to as many different events as he can, because the more events he gets to, the more people will see him, the more people will vote for him. So he wants to get to the most amount of events. But some events, there's an overlap, right? It could be that one event is at the same time as the other event, or one event starts earlier, but in the middle, the next event starts, right? So if there's any overlap, he cannot go to both events, because if he goes only to part of an event, it's insulting to those people and they won't vote for him. So his only goal is to go to as many events as he can, he has to go to the full event. Okay? But in addition, he has a superpower. He can teleport from place to place. He can teleport from place to place, and it doesn't take him any time to travel. So if a certain event ends at 12 and another event starts at 12:01, he can be there, even if it's on the other side of the world, because he can teleport. Okay? So, formally written, we're given an input, which is an array of activities, s from 1 until n, such that every single activity I, we're given si, which is the starting time, and fi, which is the end time. And the output that we're required to give is the subset, the largest subset A, which belongs to S of activities that they all sit with each other. What does that mean? Sitting with each other, that none of them overlap. Because if we have two that overlap, you can't go to both. So I mean the largest set of activities that none of them overlap. Okay? So let's just see for this example, let's say this is an optimal solution. These three activities, the most you can get here is 3. 3 is an optimal solution, and you see none of these overlap. All right. Any attempts to solve this? Obviously, a greedy algorithm. What can we do here?
He wants to go to the most events.
To the most events, yes.
Um,
What could be our greedy choice?
I mean, we could always go for A, but
Yeah, exactly. So why would you go for A? You need to explain what, because it starts first.
yeah.
Because it starts first. So the problem with it starting first is it could be really, really, really long. Could be the A goes all the way to the end. If A is all the way to the end, you take A and you're done. You can't take anything else. When really you could take B, E, and F. So you can't take the earliest starting time. Because it could be really long. Also, if you took the shortest, it wouldn't work. Why wouldn't it work? Because let's say you have two different activities. You have the shortest one that overlaps both of them. So your issue is that you take that and then you'd only have one instead of two. That also doesn't work. So what else can we do?
I mean, we know all the events.
We know all the events. We know the start time of the event and the end time of the event.
I mean, you pick all the shortest events.
No, we just said the shortest events would work.
Pick the smallest gaps between events.
The smallest gaps that also I could find you a situation that it wouldn't work. The start time, take end time. It's a clue. Start time doesn't work, but end time would work.
And you can't go in the middle of an event.
No, you have to go to the whole event. Hey, nothing. Nice to see you. It's all good. We started with greedy. We did an introduction. We did an introduction, and we started a problem. Okay, so okay. Okay. So end time would give us an optimal greedy problem, optimal greedy solution. We'll go through it now slowly of the whole intuition and the process, but think about if we took the earliest end time. That's the solution.
B.
We take B, and then C and A we wouldn't be able to take. But okay, then we continue on. Earliest end time. So we would take D, we take E, and then we take F. You can try to think of something that will like a situation that will contradict it, but there isn't one.
C. Valid.
Yes, because the second, okay, if we're taking end time, then the second we take a solution, we anything that overlaps with it, we delete because we can't take it. So we take C, E, and F. We'll go through it now slowly. All right, so you guys got it. First, let's just notice that there's some activity I that is the first activity within the optimal solution, right? So if this is our optimal solution, the first activity is A, right? What? An optimal, let's say just an optimal solution. It doesn't have to be an optimal solution we said before, but this is an optimal solution too. Therefore, we'll denote the first activity as I. Let's also note that there can't be a different activity that ends before A starts. Why not? Because it's an optimal solution. So if there's some H that ends before A starts, we could just add it to the optimal solution. And then, so our solution wouldn't be optimal. Okay? So I'm just keeping it really quickly. We're trying to find the largest subgroup that are that don't overlap. It's the basic problem. Okay, so if we have some sort of activity that ends before our first optimal solutions problem start time of the first activity, then we could just add it in. And therefore, this wouldn't be optimal. So we could just add this one in. Therefore, this can exist. Okay? And now let's note that when we choose the first activity, when we're about to choose it in the greedy, the most important parameter that we should note is the end time. It's the earliest end time, like we said earlier. we don't actually care about when it starts, but when it finishes, because it could start really early, but it could also be really long. So we want the first end time. So we're going to choose, when we choose the earliest end time, we leave ourselves with as many activities as we can, right? Because in our example, if we choose, let's say, this one, it could be that now we destroy these two options, right? That we can't take them anymore because they overlap. So therefore, if we take the earliest end time, we leave ourselves with the most amount of other activities we can take. Because it's the earliest end time, the least amount of activities will overlap with it. Okay? And therefore, at every stage, we're going to take the activity with the earliest end time, and then we're going to filter out all the activities that overlap with it, that have some sort of overlap, and then we'll continue with our greedy choice again and again and again. So let's just see how that would look. Let's say our greedy algorithm running on this example, it would choose B first because B has the earliest end time. So it'll choose B, and then it'll erase A and C because they overlap with it. And now we want to choose the earliest end time again, which is E. Even though D starts first, we choose E. So we're going to choose E, and then we're going to erase D. And then we want the earliest end time, which is F. So we're going to choose F, and then we erase G, and we are done. So this is our pseudocode. We said earlier, it's very easy to implement. Once you have the greedy algorithm, it's very easy to implement. It's like 5 lines of pseudocode. First, we're going to order the activities by their end time, right? Because we want the earliest end time. So we want the earliest end time to the latest end time. And then we're going to take the first one in that order, and we're going to add it to A. That's our first greedy choice. Then we're going to initiate J to 1. And for every I equals 2 until N, what we're going to do is we're going to compare that same activity start time and check if it's greater or equal to our activity that we chose, end time. Because if it's greater than its end time, this is f of j, right? If si is before smaller or equal to, that means there's overlap. If this is si, right, then that means that there's overlap, so we can't choose it. If it's not true, that means we can take our same I. So take I, basically add it to the group A. We're going to add it to this, and then change J to be I, because I is our new latest group that we chose. So update it to be equal J, and then at the end, after it goes through all the different activities, we'll get to the end and return A. Okay. All right, just a little note. This same greedy solution, we can describe or think of it as recursive. We can think of it as just choose the activity that finishes earliest, and then delete all of the activities that don't sit with it, that overlap, and then do that recursively, and now solve recursively this choice. It's basically the same thing as divide and conquer, but just with greedy, it's more specific, right? It's a very specific type of problem. Like divide and conquer is not necessarily greedy, but greedy can be thought of as divide and conquer. Okay? All right, so just a little side note. All right, so now we understood the algorithm. Now, how do you prove this algorithm? So we said earlier with our greedy choice property and our optimal substructure property. There's two properties that we prove, and we use them to prove the correctness of our algorithm. Okay, so let's just see those two properties. First is the greedy choice, that there exists some sort of optimal solution for our problem that includes our greedy choice. Right? That if we take the activity that finishes earliest, that it doesn't ruin our chances, our optimal solutions. Right? That there still exists some optimal solution with our greedy choice. So that's the first level. That there exists some sort of optimal solution that includes it. The second property is the optimal substructure. which is basically that given a greedy choice and a recursive solution, an optimal recursive solution, on the subproblem, if you combine those together, you'll get an optimal solution for the main problem. Okay, and we'll prove that one afterwards, and we'll go into its definition. But first, let's just look at the first one and prove the first one. Okay, the greedy choice, like we said, it's just there exists an optimal solution that includes our greedy choice. So in our problem, in our greedy algorithm, what's that choice? It's the earliest ending activity, right? So we want to prove that there exists an optimal solution to our problem, to the activity choosing problem, that we choose the activity that finishes earliest, right? That's our property that we want to prove. We'll call it also lemma 1, just to be able to reference it later. Okay, so proof. It repeats itself. The structure of the proof really repeats itself. I did a whole slide at the end, or one slide I show you the proof of both of them, just the structure of them. But when you do it formally, it will be a little bit longer. So let there be some sort of optimal solution. Okay, if the activity that finishes earliest is included in opt, we're done, right? Because that's what we wanted to prove, is that if we take our greedy choice, that there exists some sort of optimal solution that includes our greedy choice. And here we're saying that if the greedy choice is within opt, we're done, because we basically proved what we wanted to prove. A lot of times they skip this step, but it's an important step. But sometimes they skip it. That's very trivial. If it's in the opt that we just took, then we're done. So let's just assume that it's not in. So if it's not in our opt, what we're going to do is let's look at J. And J is the earliest ending activity in opt. So it's not the first one, right? Because it can't be the first one, because that would be in this case, and now we're in a different case. So it's something other than 1. Took something else. So now we know for sure that J finishes after F1, because we know that 1 finishes earliest. So J has to finish after. Now we're going to do, and it's the same exact format that we say, let's build a new opt solution with our greedy choice. Let's take this opt solution that doesn't have our greedy choice. Let's take away some other choice that isn't that good. And let's add in our greedy choice. And then this opt tab, we'll see that it's optimal. That includes our greedy choice. If we prove that this is optimal, then we're done. We proved the lemma. Okay? So we need to prove 2 things. We need to prove that it is a valid solution, that we didn't bypass any constraints, that we didn't go over any constraints, which in this case is just that we don't have any two activities that overlap. Okay, and also that it's optimal. And you can see that this is very, very similar to proving correctness in dynamic programming, right? Proving that it's valid and optimal, something that kind of appears quite often. Okay, so how are we going to prove that it's valid? Let x and y be a pair of activities in up time. If they're both not the first activity, x and y don't equal 1. They're not the first activity. So therefore, they're both within opt. And if they're both within opt is valid, right? And if they're both within opt, that means that they both have to sit with each other. They don't overlap. Because opt is valid. If else, let's assume without loss of generality that x is 1. X is the first activity. Without loss of generality, we could have done y, but it's the same, so we don't lose our generality of our proof. So we can say that x equals 1, and let's say that x sits with y, that they don't overlap. So j and y belong to opt. Now remember that j is the first within opt, right? That we took out, right? And so therefore, f of j is definitely smaller or equal to s of y, right? Because j and y are both within opt. So therefore, f of j has to be less than s of y, because otherwise they overlap. And one, what?
Star.
S of y is the start. F is the finish, and S is the start. So the finishing of j is small or equal to the start of y. And now let's note that 1 is the earliest ending activity. So therefore we know that f of 1, the finishing time of 1, is earlier than f of j. And we know f of j is smaller or equal to s of y. So therefore f of 1 is smaller or equal to s of y. And therefore they don't overlap. Right? Therefore they don't overlap. Therefore they
Nice.
sit very nicely with each other. And we are done with proving that it is valid. All right. Usually the proofs are the same. It's the same structure, just different problems. And we'll see also in the next problem that it's the same. But now let's prove that opt is optimal, right? Second thing we need to prove, once we're done with this, we're done with the lemma. We prove the lemma. So it holds that optag equals regular opt without j with 1, right? This is by definition how we built opt child, right? And this equals to, if you take the size, right, it's just the size of opt without 1. Sorry, because we took away a choice. We took away an activity, so minus 1. We added in an activity, so plus 1, which equals opt. So therefore, opt tag equals optimal, and also our solution that we created is also optimal. Therefore, opt tag is optimal,
That's it.
and that's it.
Oh my god.
That's it. Yep. Very, very short. So we are done proving the first lemma, which is the greedy choice. Okay? But now we need the other one. Any questions on the first one? Yes.
I don't question.
Okay, but you had a question?
This is the first.
The first lemma is the greedy choice. The first one is the greedy choice, which is there exists some sort of optimal solution to a problem where we choose the one that ends earliest.
Yes.
That there exists some sort of optimal solution. Exactly. This is lemma 1. So the 2 we're proving now. The second one, we're proving it now. Exactly. So with our first lemma, with the greedy choice property, we're going to prove the next one. So you have to prove that one and then prove this one. Okay. And it's basically this one is equivalent to the step of the induction. It's not equivalent. Sorry, it's parallel. It's similar to the step in the induction. Because right, the first one was just there exists some optimal solution. The second one is the step is ready. If you combine it with an optimal sub solution, you'll get an optimal solution. Okay, so the second lemma, the optimal substructure, a solution that is built from our greedy choice, and then also optimal solution for the subproblem without our greedy choice, together is optimal. So in our case, it would be a solution that is built from the choice of the activity that finishes earliest, right? It's the choice of the activity that finishes earliest, in addition to an optimal solution to the problem of choosing the activities, but with all of the activities that don't overlap with our greedy choice, because we can't use them because they overlap, so we kick them out basically, and we say if we have an optimal solution to that subproblem and we add it to the greedy choice, then that in itself is an optimal subproblem and an optimal solution to the whole problem. Okay, understood? All right, because it's important to understand what we're proving before you prove it, because it might be hard to follow. So no questions on this, so I'll go right into the proof. So it's also the same structure. The proof is, let's assume for the sake of contradiction that the algorithm that is described in this lemma, we'll call it A, is not optimal. And therefore, there exists some B that is optimal, right? And the size of B is greater than the size of A. So we assume for the sake of contradiction that there exists some B. Now, with that loss of generality, according to the greedy choice property that we already proved, the first activity is within B. Why am I allowed to do this? Because without loss of generality is basically saying I'm gonna take a specific case of all the different cases, but I'm allowed to do that for some reason, and it doesn't ruin my proof. Doesn't ruin the generality of my proof. So because of the greedy choice, I know that there exists some optimal solution with my greedy choice, right? So therefore, I can say, okay, I'm going to take that specific optimal solution. That one that includes my greedy choice, I'm going to take that one. If we didn't have the greedy choice, we couldn't do this because we don't know that there exists an optimal solution that includes our greedy choice. So because we know it exists, we're just going to take that one. Okay, so that's what we're doing here. And because B is a valid solution to the problem, all of the activities that start before F1 are not in B. They can't be within B, right? Therefore, also A without the first activity and also B without the first activity are solutions to our problem with only the activities of all the different activities such that the starting time of the activity is greater than the finishing time of the first one. So this is all activities that don't overlap with the first activity. So these two are optimal subproblems for this one, right? And the size of the solutions are A minus 1 and B minus 1 because we took away one of the activities. And now note that because of the definition of A, because in the lemma we took a solution that is built from a greedy choice and an optimal solution for the subproblem, right? This is the subproblem. A without 1 is the optimal solution for the subproblem, right? Just based on the lemma that we took, the solution we took, A without the greedy choice is optimal. Okay, so therefore A is optimal. A without the first choice is optimal for the subproblem. Therefore, A minus 1 is greater equal to B minus 1 because we know that A without the first choice is optimal. Okay, so now that we have this, we know that A is greater equal to B, which is a contradiction to our assumption. So I'm going to go through it again quickly because I know this was a lot to follow. So we're trying to prove in our lemma a greedy solution based on the greedy choice and optimal solution to the subproblem after a greedy choice together builds an optimal solution to the problem. Okay, so we assume for the sake of contradiction that whatever is described in the lemma, A, is not optimal for the whole problem. Remember, it's built from a greedy choice and optimal subproblem. So A without 1 is optimal for that subproblem. That's what we use afterwards. So, and then we assume that B is optimal solution. We can say that 1, it belongs to B because of our greedy choice property. So we can say that 1 is within B. So therefore, 1 is within B and 1 is also within A. So therefore, we can say that we can take away 1 from both of them because we know that 1 is within both of the solutions, right? So we can take the greedy choice away from both of them. And then we know that our solution from the lemma without the greedy choice is optimal. So we use that, and we basically say that A without 1 is optimal. Therefore, A minus 1 is greater or equal to B minus 1. And then we add back in our greedy choice, right? Basically just adding 1 on both sides. And we see that A is greater or equal to B, contradiction, because we assume that B was strictly greater than A. Okay? So that's basically the same exact format that we assume. Let's take a contradiction that it's not optimal. So let's take an optimal solution. We take away the greedy choice from both of them. And then we basically use the lemma that this is optimal without the greedy choice. Ours is optimal. We add the greedy choice back and we get a contradiction. It's the basic format. And so we prove the second lemma. Now we need to finish the proof. What does that mean, finish the proof? Basically, the reason that we prove those two things, they don't prove the algorithm just like without anything. We need to prove the algorithm, right? So how do we prove the algorithm? Now with those two lemmas, what we can do is we can do an induction on the input size and use those two lemmas to very simply prove the algorithm with induction. Without those lemmas, it would be a little bit harder to prove it with induction. And induction, once you have those two lemmas, it's the same exact induction. It's literally the same exact words. So I'll just show you how to do it. The base is a group of just one activity, which is, it's obviously correct because you just take that one activity. That's all you can take. You're done. That's optimal. Right, your choice would choose it. It's optimal. Very trivial, usually the base. And then the assumption, let's assume that the algorithm finds the largest group of activities that sit together that don't overlap for every n hug smaller, strictly smaller than n. And now let's prove for n, for a group of n activities. Okay? So here's the step. Let there be an input size of n, but according to the greedy choice, there exists some sort of optimal solution that includes one, right? Just that's by the first lemma. That we prove that include, like with our first choice, that there still is an optimal solution, right? So after choosing one, there still exists an optimal solution, and also after our choice, we have n tag smaller than n different activities, right? We have basically a subproblem with a strictly smaller than n amount of activities because we definitely took away one for the first activity. Could be that we deleted a couple more that overlap with it. So, but we know that it's less than n. If it's less than n, we can use the induction hypothesis, right? Use the induction hypothesis. The algorithm finds an optimal solution for us, an input size of n tab. And then if it finds an optimal solution, we're going to use our second lemma, which takes an optimal solution for the subproblem plus our greedy choice, and together it is an optimal solution to the problem. Okay, it's the same. This is literally, it's the same induction every time. It's just first you're gonna let there be some sort of input. After, and then you use the greedy choice algorithm, the greedy choice property, to say that there exists some optimal solution with our choice. And then after that choice, you have strictly less than the original input. Then you can use the induction hypothesis, then use your second lemma to prove it. Questions on the proof? Because I know it was long. Okay, no questions.
My brain just left alone like half an hour ago. Yeah, so we proved that greedy choice works. It's in the solution, and then we find the best solution by proposing a solution, then saying some solution is better, and taking the greedy algorithm.
That's how we proved it.
Yeah.
It's how we proved the greedy choice. Yeah. So we proved the greedy choice, which is saying that there exists some sort of solution with our greedy choice, some optimal solution with our greedy choice. And the second one is saying that given a solution, kind of like in divide and conquer, that given an optimal solution to the subproblem, if you add back in your greedy choice, you'll get an optimal solution. It's kind of like the step in the induction. It's given a smaller one, and then add in your greedy choice. That together is optimal. And you see, we actually do that in this step. That's our step, is basically using the second lemma. Okay, so we're going to sum up how you prove greedy algorithms. So the first one is the greedy choice property, which there exists an optimal solution that includes our greedy choice. The second lemma is the optimal substructure problem. Optimal substructure property, which is basically a solution that is built from our greedy choice, and an optimal solution to the subproblem is in itself optimal. And then we have to finish the proof with induction on the input size, and we're done. All right, so if you weren't paying attention, it's okay. We're starting a second problem for today. second and last problem. So let's do this. So this is knapsack problem with fractions. Like you can take part of the item. So let's just tell the story. A robber breaks into a pharmacy and he has a knapsack. In the pharmacy, there's n different items. For every item I, it has a weight and a value, and the robber can take items that their weight is not more than B. You can only pick items up until B. Only once we did this, but now we have a little twist. The robber can take parts of items. It's the fractional knapsack. The robber can take parts of items. He doesn't have to take the whole item, right? Knapsack, we did knapsack, the whole knapsack. We have to take the whole item, right? So that's also what this slide is about. So remember the knapsack. With integers, we have to either take the whole thing, take the whole item, or not take the whole item. In the fractional version, we can also take part of the item, and the value of the item is proportionate to the amount that we decide to take. Right? So if our item has a value of 30, and we decide to take a third of it, we get 10. The item doesn't lose any value or gain any value if you take part of it, right? It's just proportionate. Take a third, you get 10. So formally, it's written as such. The input is an array of prices, an array of weights, and the maximal weight that you can take in his knapsack, G. The output that we want is an array, is a set such is x, which equals to x1, x2, x3, x4, and each xi is between the range of 0 and 1. Okay, this tells you how much of the item you're taking. So if x1 equals 0, it means I'm not taking any of the first item. If it equals 1, what does that mean?
Okay. We take the whole item.
We take the whole item. Okay? And also we need our solution to hold that we didn't pass our maximal weight, right? We didn't pass our maximal weight B. But here, it's not just summing up the items we took, it's not just summing up their weights, it's summing up also the amount we took of each item, right? So if we took half of an item, we will add half of its weight to the sum. So that's just what's written here is take the amount that you take from every item, times it by its actual weight, sum that up for all the items, and that has to be smaller or equal to B. And the value of the sum of all of the VI's is greatest. Okay? Of all that, I think there's missing a WI times VI here. Is also proportionate to what you took. Is the problem well defined? Is it? Yeah. Any questions? Thomas, I know you know you have this problem, so.
No, I
it's
know
well
it.
Defined.
I know it because of told me about it yesterday.
Who did?
Alba.
Oh yeah? Haha. Okay. So I'm gonna continue if there's no questions. Any suggestions of how to solve the fractional knapsack problem? If you know the answer, Thomas, then don't answer. But if you don't know the answer, I'd love for you to answer, Thomas.
Maybe we can just take the whole item first.
The whole item?
Yeah, why not?
What do you mean the whole item?
You didn't want me to tell you the answer, so I just.
Oh no! If you know it, then don't answer. But if you don't know it, then you're welcome to answer. What any suggestions? Any suggestions from the crowd? Remember also what we did in the whole knapsack. Right, when you had to take the whole item or not take the whole item, so you just did a couple of things there. And those were in fact greedy solutions, but they just didn't work for the knapsack where you have to take the whole item. They only work for the fractional knapsack. So no suggestions, so I'll suggest something. What if we take the most that we can from the item that's worth the most? So let's say if we have a couple items, we have a weight and a value, right? The value is, let's say, 50 of the first item, and the weight is 50. And then the next is 40 per value and 30 weight, and so on and so forth. And let's say we have 20 and 10. Sorry, that's not what I wanted to do. Say this is 10 and this is 5. And we have a knapsack of 65. So let's first take the one with the largest value, and we take the one with the second largest value. We can't take it. Oh, we can take it. Say 55, so we can't take a specific amount. We can't take this one, and we can only take 50 and 5. It works here. Why wouldn't it work? It's taking the highest value.
Seek out higher weight.
Exactly. It could just take up all your weight. Let's say our knapsack was 100. And the value here, let's say, is still, so this is 60, and then we have 2 50s, right? Even though this is the highest value, I could get, let's say, 2 40s, or even 40, 45. If I took this one, it blocks me from taking the other two. Okay? So for this example, we wouldn't want to take the highest value, we'd want to take these two. So what can you propose after this? The ratio, exactly. We want the highest ratio of value to weight, right? And we can take as much as we want. That's the difference between this and the whole knapsack problem. So we can take as much as we want. So we'll basically take the one with the highest ratio. In this case, it's the 45/50 is the highest ratio. We're going to take as much as we can from this one, and we'll take as much as we can from the next one, and so on and so forth till the backpack is full. Okay, so that's the solution. Let's order all of the objects based on what you said, the ratio. The ratio will denote it as AI, which is the value divided by the weight. And we'll also order all of the items such that we'll get the first item is the highest ratio, the second item is the second highest ratio, and so on and so forth to the lowest ratio. And afterwards, we're going to greedily take the items. Starting from the one with the highest ratio, we're going to take as much as we can, fill up our backpack as much as we can. If we still have room, we'll move on to the second item and take from it until our backpack is full, and so on and so forth until our backpack is full. So the pseudocode is for every I equals 1 until n. Calculate the ratio, and then we're going to order all of the elements according to their ratio, from the largest ratio to the smallest ratio, and then we're going to start going through all the items, and we're going to take the minimum between B, how much room we have left in our knapsack, and its actual weight divided by the weight. So what does this mean? Basically, if we can take the whole item, we're going to take the whole item, and then it would be weight I divided by weight I, which is 1. And we're going to put 1 into the xi, which means we take the whole item. If we don't have enough room in our backpack is smaller than the weight of the item. So therefore, we can only take up to B. And how much of the actual item are we going to take? We're going to take B divided by the weight of the item. So that'll give us, when we times it by the weight of the item, it'll give us B. And our knapsack will be completely full. So that's why we're taking the minimum between B and WI. So we add that into xi, which is how much of the item we're taking. And then we subtract from B the amount that we took from that item times the weight of the items. And we put that into B. And we continue in a loop through all the items. Even once B hits 0, we just keep on looping through. And we'll just take 0 divided by WI. And all the rest of the items will be 0 the second we finish. And at the end, we just return our array of xi's, right? Pretty simple algorithm. Once you understand that, once you come up with the greedy choice, like the what you're going to choose greedily, then the algorithm itself is the easy part.
Yes, it's the easy part.
The proof is a bit harder, but if you do a couple of problems, it's the same exact structure. And at the end, I have one slide where in one slide I wrote the structure of both proofs in one slide. So it's pretty straightforward. What are you gonna ask? You want to say something? Okay, you're gonna say it's hard for you.
Yeah.
Okay, so try and try and like pay attention for this one. Try and be with me for the whole one, and then you'll see it's a bit easier. Okay. Okay. So also a little bit of a side note, like you said, you can also think of it as a recursive solution. Right? Our greedy algorithm can also be thought of as recursive. And each time we take the most we can from the highest ratio item, and then recursively call the problem on the rest of the items until we don't have any more items. Okay? All right, so number three, why three? Because we already had 1 and 2 for the previous problem. So number three, but it's the same first property, which is the greedy choice property. So in this problem, what is the greedy choice? That there exists some sort of optimal solution to the fractional knapsack that we choose the highest amount that we can take, the highest amount that we can take from that highest ratio item, which is A1, right? Because A1 is the highest ratio, so the one with the highest ratio, we take as much as we can from it. And then that is our greedy choice, and there still exists some sort of optimal solution. So how are we going to prove this? It's the same thing that we did earlier. So here we're only going to do the idea of the proof, and I'm going to verbally say it, like the formal proof, because just writing this one out is very, very long. It's a lot of notations and stuff, so we didn't want to confuse everybody. So we're just going to explain the idea of the proof, okay? So we're going to look at some sort of optimal solution, x tag 1, x tag 2, until x tag n. Okay, so we're going to look at this optimal solution. And now we're going to say if the greedy choice is within it, if we take as much as we can, if x1 tag equals the most that we can take from x1, then we're done, right? If it is according to the amount, if it is according to the property, then we're done. If not, then let's build a new solution, right? Let's build a new optimal solution. Let's kick out some other choice, right? Some let's say if he chose more of xn, then let's kick out that amount of weight that we need and add in the weight that he didn't take from x1, which is the highest proportion, right? It's the highest proportion. So if we pick out the lowest proportion or some other proportion and take the same amount of weight, but from x1, we'll get a solution that is also optimal, right? You have to prove that. Don't you see that? Yes, Thomas?
X1, X2, whatever is sorted already, so X1 has the biggest ratio.
Yeah. Yeah, x1 is sorted, you can see sorted.
So like we know that the biggest ratio is to the left. Like the first ones have the biggest ratio.
Yeah, exactly. I'd have to write it formally, but that's also why we we just kind of like wrote the idea of the proof, and I'm gonna just say it like verbally. You're right, you have to denote like this in their order of sorting, right? So on and so forth. Okay. Elsewise, let's just see that we can trade some sort of other choice that he has, some sort of other object, with the rest of what's left of x tag 1, as much as we can switch, right? So if let's say there's 4 kilos of the first item that he didn't take. So let's kick out 4 kilos of some other item, and let's add in our first item. Okay? So that's basically what we're saying here. And then we want to say, and then at the end, we just need to prove that this new solution is optimal, and that it's valid, and that it's actually optimal. So it's valid, let's just say it really within 2 words. It's valid because we took away the same amount of weight that we put in, so the weight stays the same, and therefore it's still valid. We didn't surpass B. Right, because we took the 4 kilo away, let's say, and we added 4 kilo in of our highest ratio item. The value changed. It didn't necessarily change. We're assuming it's greater or equal, right? Because it could be that there's all the items have the same proportion, right? So it could be that they have all the same proportion, it's greater or equal, but we don't care because it's still optimal, right? So then that's how you prove optimality. If you say take away 4 kilos of something and adding in 4 kilos of something that's greater or equal to in value to the other one is still optimal. It's greater or equal, and therefore it's still optimal. So if you needed to prove this formally, you'd have to do a little bit more, denote it as this, its order, blah, 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 take this item or whatever. It's a bit more complicated formally to denote it, so that's why we just said it verbally, because the idea of it is very, very simple. All right, so now let's do this one formally, okay? So the optimal substructure property, a solution that is built from our greedy choice, and then an optimal solution to the subproblem without our greedy choice. So that an optimal subproblem on the rest of the items with a knapsack, which we subtract from it the weight that we took, right? So if we're given an optimal solution on that subproblem, we already took as much as we can from the first item, together with our greedy choice of taking as much as we can, together is optimal. Okay? This is the same exact lemma, just for a different problem. So the proof is the same. Let's assume for the sake of contradiction that it's not optimal. And therefore, let's assume for the sake of contradiction, whatever is described here is not optimal. Let's denote it as this. And let's assume that this is optimal, that there exists some sort of other optimal. And what's the next step? The next step is always saying, according. Well, first we need to do is use the greedy choice lemma and say that we're going to take, without loss of generality, we're going to take the solution with our greedy choice, which is taking as much as you can from that highest ratio item, right? So without loss of generality, x tag 1 equals x1, right? Because this is our greedy choice. And we can basically take the optimal solution that takes the most from the first highest proportionate item. Same thing as our previous proof. Is that understood?
So we just prove that the x1 tag is equals to x tag x1, and then we just look at the subproblem after that, right?
You're going now to the continuation?
Yeah, no, I'm saying like what
we did until now?
What we did until now is like we said that it doesn't have x1, and then we prove it does have x1. It's the same.
Not what we're saying. We're saying basically it's assuming this what we described in the lemma is not optimal. If you take a greedy choice and an optimal subproblem and put them together, it's not optimal. Let's assume for the sake of contradiction it's not optimal. So therefore there's something else that is optimal. By the greedy choice property, we can say that x1 has to be our greedy choice.
Okay, sure.
We can take that solution. It has to be our greedy choice. Okay? And we can do that because we know that the greedy choice means that we know that there exists a solution with our greedy choice. Let's take that one. We know that there's an optimal solution with our greedy choice. So we take that one where x times 1 equals to x1, which is basically taking the most that we can from the highest ratio. Right? That's our greedy choice, taking the most we can from the highest ratio. So therefore, both of them from x2, right, are both solutions to the knapsack problem, fractional knapsack problem, but without the first item, without the high proportionate item. And also with the knapsack, which is subtracted, we subtract from the knapsack the x1, the amount that we take, times the weight. So we subtract the amount of weight that we took. So both those are solutions to this. Now, what do we know about this solution? It's optimal, exactly. It's optimal because it's what was described in the lemma. And the lemma is taking a solution to the sub problem without our greedy choice, which is this. We know that it's optimal. So therefore, we know that this is optimal, and therefore the sum of xi times vi of our optimal solution is greater or equal to the sum of x tag I times vi. Because ours is optimal, it could be this one's also optimal, but ours is optimal. So it's greater or equal.
Where do you state that the subproblem is optimal? Like you have an optimal solution for it?
So it's in the lemma. The lemma is if we take a greedy solution and add to it the optimal solution of the subproblem without the greedy choice, those two together are optimal. So we know that without the greedy choice, it's optimal. That's what we assume. In addition to the optimal choice. Yeah, in addition to the optimal solution to the subproblem. Okay, so that's where we know that our solution is optimal once we take away the greedy choice. Okay? And now bear with me. It looks complicated, but it's not complicated. Therefore, also after we add in the x1 to each of them, this looks complicated. Don't be scared. It's really simple. We have the sum from x1 until n, right? Which equals 2. Let's take away the first element. And this is what we already said was greater or equal to this one, right? To x dot. That's what we said earlier. Because this part is optimal. It's greater or equal to this. And this stays the same.
Yeah.
And we also know that x tilde 1 equals x1. So therefore we can do this. This next step, which is just switching x1 with x tilde 1. And therefore this also equals to just the sum from 1 to n of x tilde times vi, which is the solution that we assumed is optimal, is more optimal. We assume this is strictly larger than this, and now it's smaller equal, which is contradiction. Okay, it's the same exact format. I'm sure now it's like ringing some bells from the previous one, where you're like, oh, that kind of makes sense. We did that earlier. But yeah, so we just proved the second lemma too. Any questions? Okay. Once you do a couple of them, I have to say it becomes very intuitive and it's the same structure, and you can just do it by yourself. It's very, very intuitive. Just doing it formally sometimes is the tough part. So now we have to finish the proof, and how do we finish it? With induction on the sides of on the input sides, right? So the base, if we only have one item, the algorithm chooses the minimum between one, but taking the whole item, and the knapsack divided by the weight. Therefore, if our knapsack is smaller than the weight, then we'll take some sort of fraction that fills up our knapsack. Okay? So we'll take that, and that obviously is the optimal solution because we just take as much as we can from the only item, which is obviously optimal. And then the step, let's assume that the algorithm finds an optimal solution with an input size of less than n, and that's proved for n. So from the greedy choice algorithm, there exists an optimal solution, x star, with the greedy choice, which is x1 star, which is as much as we can from that first item. The algorithm chooses x1, which is the minimum, and continues to the subproblem of n minus 1 items, and a knapsack, which now we subtract the amount that we took from that first item times its weight. So we subtract the amount of weight that we took, and now we know from the induction hypothesis that we have an optimal solution to this subproblem because it's from the induction hypothesis. It's less than n, so we know there's an optimal solution, and so our algorithm finds the optimal solution based on the induction hypothesis, and therefore from the optimal substructure, this optimal solution to the subproblem, in addition to our greedy choice, together is optimal. That's our second. That's our fourth lemma. The optimal substructure, and therefore we finished our proof of the greedy algorithm. The induction is the same. Little side note on the induction is in a lot of places you'll see that they don't even do it. They prove the two lemmas, and that's it. Why do they do that? But it's the same exact thing in the induction, and they assume that you know how to do it. It's more formal. This is the whole proof. But a lot of times, even in the test, if you don't have time or you don't remember this, if you don't do it, a lot of times you'll see in actual answers from tests that they don't even do this. I would do it because it's the formal way of doing it, but it's up to you. I'm just putting it out there that a lot of times you see they don't do it because it's the same exact thing, and they want to see that you can figure out the greedy algorithm and prove the two lemmas. Okay. So here's the slide that I promised you, where it's just the structure of proving the two lemmas. So first we have our greedy choice lemma, right? That there exists some sort of solution, some sort of optimal solution. It starts from our greedy choice of our algorithm, right? That there exists some sort of optimal solution, including our greedy choice. So how do we prove that? First, let opt be some sort of optimal solution. Now what do? Okay.
We take out something.
Exactly. It's a lot of times the thing is where we take out something and we add in something.
Yeah.
But before we do that, we can say if our greedy choice is within opt, we're done.
Yeah,
Right?
I know.
Exactly. It's just like the little step.
Forgot.
If it's within opt, we're done. And if not, what do we do?
We take out something, the first one.
Not the first one. We want to add it in. We want to add in the greedy choice, right? Right now we're saying elsewise it's not in. So we want to add in the greedy choice. We got to take something else out, right?
Yeah.
So let's add it in our greedy choice. Let's build a new opt tag solution, which is opt without some sort of other choice or choices. And we add in our new choice. Okay, so it could be we take out a couple, but we only have one in. And therefore, then we need to prove that opt tag is valid and optimal. And it's very simple to do because we just use opt to do it. Okay? So that's how you prove the first lemma. Pretty simple. Now the second lemma, the optimal substructure. A solution to the problem, which is built from the greedy choice, and also an optimal solution to the subproblem without our greedy choice, is itself an optimal solution to the whole problem. Right? Greedy choice, subproblem. If we're given an optimal solution, we add the greedy choice and it's optimal. So how do we prove this? Exactly. Assume that whatever is described is not optimal. Very good. So let's assume that it's not optimal. And therefore we have some sort of opt that is optimal. And therefore I kind of wrote smaller, strictly smaller, or strictly greater. Okay?
Or I could just,
What do you mean the greedy algorithm?
based on the previous lemma, we know that there exists an optimal solution, including this greedy choice. And say that this group is one of those examples.
Say that again?
Based on the previous.
Based on previous lemma.
This solution,
Exactly.
including our greedy choice.
Exactly. So you're saying the next step already.
I'm saying that my B that is more optimal item includes.
Exactly. We know that the opt includes our choice.
Yes.
Exactly. Yeah, correct. That's the next step.
Do I have to be explicit about the? Okay.
Yeah. Because otherwise you don't know. You could prove it some other way. This is just the format that I'm giving because it's just the general format. You could also just assume you don't have to do like what you said where you just use the first lemma and then say that our greedy choice is within opt. You could kind of just it would be longer if you didn't use this. It would just take you longer to prove because you'd have to like look for some other thing and add in your greedy choice like we did here. You'd have to do this whole thing again. Okay, so instead we just say with Alice generality, we'll use based on the previous lemma, the greedy choice is within it. And then you just go back one choice, let's take away the greedy choice from both up and A, our solution and the optimal. We'll just take away the greedy choice and this from the lemma, we know that A without our greedy choice is itself optimal.
Yes.
And then we know that once we add back into A our greedy choice and back into opt our greedy choice, then we get that A is either smaller or equal to opt or greater or equal to opt, depending on if it's a min or a max, which is a contradiction to our assumption. And then we prove the second lemma. So this is the format for proving the first lemma and the second lemma. Right? Some problems might be a little bit different. Every problem, valid and optimal is always different, but it's the same format, and it's very worthwhile to remember this because it shows up a whole lot. Okay, summing up the recitation, the greedy algorithms. What is their I don't want to say come on, but basically how greedy algorithms work, we choose some sort of local optimal choice at every single stage, and we hope that we'll get to an optimal global solution. They'll tell you why in the beginning, but we also want to know this in the beginning, that we just try and choose an optimal solution based on the information we have right now. And we hope that in the future that'll lead us to an optimal solution. And we said that not every single problem has a greedy algorithm, because not every problem this will work. In whole knapsacks, they wouldn't work, right? In whole knapsack, it doesn't work because it could be that even if you take the highest ratio,
It could be, let's say, even if this is right now 70, we took the highest ratio, which is this one. If we can't take part of the next ones, then we're blocked, right? Because once you take 60, you can't take 50 and 50.
Yeah.
So the greedy choice does not work in the knapsack where you can either take or not take the item, because you get blocked in certain cases. So therefore, you hope that in the end it'll get you to a greedy solution. But how do you know it gets you to a greedy solution? Is you prove the two lemmas. To prove the two lemmas, you know it works. So some advantages of greedy algorithms, they're very simple to implement and also to think of. It's just a greedy choice. They're very, very efficient. They don't take much memory, any at all. The biggest disadvantage, though, is not every problem has a greedy algorithm solution. And therefore, we need to prove that the solution really exists. A little bit of intuition also of when you try and solve greedy algorithms, if you can solve it or not. You want to look at your greedy choice. And if that choice is optimal, basically because it's kind of hard to prove that something doesn't have a greedy algorithm, right? It's very hard. So what we do expect you guys to know is, given a problem, think of the best greedy choice, right? You can think of what is the optimal choice locally, and then see if that leads to a solution for every case. Because in certain cases, the greedy choice will lead to certain, even in knapsack, let's say, where it doesn't have a greedy thing, a greedy solution, it could be that a certain case will lead to an optimal choice, right? It could be that this is 10 and this is also we can leave it at 45, and really the optimal is choosing this, right? But if you have to, when you take your greedy choice, think about cases that might contradict it, right? You try and contradict it, and if you can contradict it, it doesn't work. But if you can't figure out a way to contradict it, then probably you can prove it. So that'll give you a little bit of intuition to then jump into the proof. If that's also, if it doesn't say solve it using a greedy algorithm, it might say solve it using a greedy algorithm, then you know it exists. Okay, so we are done for today. If you have any questions on greedy algorithms.
Are you planning a homework for this? Probably not.
About the test.
So about the test. Okay, so first of all, about homeworks, I'm gonna upload today. I'm gonna upload. There's two homeworks: the dynamic programming 2 and greedy algorithms. We were supposed to have dynamic programming 2, but because things got delayed, we were supposed to have 12 assignments this semester, and then we only have 11. We only have 11, and you only have to do 9. What? Yeah. So I'm gonna upload it. I thought maybe I would translate it. I don't have time savvy though to translate it. I uploaded the what was supposed to be the homework, and also with the answers, so you can check yourself. You can try and solve it and check yourself. So that for dynamic programming and for greedy.
Okay.
Okay, about the test. Do you guys have any questions before I go on my spiel? Before I talk about the test. Do you have any questions about the test? No?
Yeah, I have a question.
Okay.
But maybe you're going to answer.
No, I'm probably not gonna answer. What I was gonna
No, it's
basically.
not question. It's not the development bit.
כן.
אני לא מבינה, כאילו עוד לא כתבתי מבחנים בכלל, אז אני לא יודעת כאילו למה לצפות במבחנים, אבל זה ברמה של כאילו, אני לא יודעת, אם אתה שוגה בפסידוקוד, אם אתה פתאום כאילו לא עד הסוף כאילו, זה סתם בוא נתמד כמו שצריך, אני לא יודעת כאילו עד איזה רמת דיוק אתה צריך להגיע במבחן הזה. כי פסידוקוד זה כזה, זה חפיף, כאילו זה נראה חפיף, אבל אז אני לא באמת יודעת, כאילו דבר כזה, שאלה כזאת, אז יהיה לי 4 שאלות כאלה לענות עליהן, או שאלה אחת?
שאלה אחת, עם גרידי זה לרוב שאלה אחת.
כי זה שאלות נורא ארוכות.
נכון, לוקח את זה לוקח זמן.
זה לוקח מלא זמן.
ברור, לא יהיה לך 4. גרידי יכול להיות שיש לך סעיף א' שמכווין אותך לסעיף ב', זה לפעמים כן עושים, אבל לרוב זה אלגוריתם אחד.
יש לי עוד שאלה.
אוקיי, also I'll answer in English, sorry.
מאוד עובדת על לראות כאילו איך כותבים את האלגוריתמים, יש כל מיני הרצאות, הכנסות, כל מיני דברים כאילו אפילו פשוטים שיהיה לי בראש פחות או יותר. אבל זה דברים שאנחנו נידרש לכתוב אותם, להסביר אותם במבחן, כאילו.
Something that we learned in the lecture recitation, let's say AVL,
Yeah.
you have to. So if you just have to use AVL, you don't have to explain. If you say we're using something that we learned in the class, that's it. You don't have to prove it. You don't have to explain it. Nothing.
אוקיי.
But if you change it a little bit, you have to explain the changes that you made. And we might ask a question that you need to understand how it works in order to solve the question. Like you have to use AVL, but you have to change it a little bit. Or we might even ask questions, given an AVL tree, how the rotations work. We might ask you.
Remember to write the dictative. Find AVL, I don't know, child or.
So anything in the material that could be theoretical analysis. I haven't seen the test. That's also what I wanted to say. I haven't seen the test yet, so don't ask me questions about the test specifically. And I'm also not going to tell you anything but what I do see. But anything that is in the material could be on the test. They could ask, write pseudocode for AVL insertion. It could be. But what's more likely is you'll look at previous tests and you'll see the kind of the format. Most of the time it's write me an algorithm that does this and this and this. Write me, they support a data structure, build a data structure that supports these operations. And so on and so forth. Sometimes ask about the lecture and they'll have you they'll test if you remember the lecture. You do also need to remember the lecture. There's two kinds of questions. Yes. So I recommend, like I said last time, going through the topic by topic, going over the topic, solving the questions, making sure you understood the topic. And then only after you go through all the topics, you start solving full tests. Now, a few other tips that I have. Like we said, there's two types of problems that either you have to use the algorithm, you have to make an algorithm or a data structure, and then you kind of do something similar to what we did in the lecture or the recitation. A little bit of a change. Or there could be a question that's like, do something that we did with like, let's change a little bit of a parameter. Let's say in the homework there was a question, you remember Karatsuba's algorithm where it's multiplication between two numbers. We split each number into two.
Yeah.
And then we kind of do a smart divide and conquer. And so there was a question on the test where I also put it in the homework where they asked divide it into three numbers, not into two.
Yeah.
And then how does that affect it? So you have to remember the lecture, right? You can't just, if you don't remember the lecture, it's kind of hard to do. So you also need to know the material and also you need to know how to use the stuff that we taught. So you need both of them. And then, just solve it topic by topic over the material. And and hope for the best. All right, I guess we're done for today if there's no more questions. You're welcome.